Hello and welcome to very first lecture of this digital image processing course. In this particular lecture, we will talk about image, like how can we define image, and by default images are analog, how to transform, how to convert images from analog into digital nature, and in what particular format images are stored in computer memory. So, like from very simple definition, let us start with a simplest definition. An image can be defined as a projection of 3D objects on a 2D surface. As we are living in 3D world, everywhere we can see that the position of particular object in this real world, this is to be measured in terms of x, y, z. The dimension of any particular object in your surrounding, this is to be computed, this is to be measured using x, y, z. Maybe you do have your lunchbox, maybe you do have an empty container of your CPU, empty box of your CPU, maybe your laptop. If we want to measure dimensions, definitely it will have something on x, something on y, and something on z. Even human body dimensions, definitely this is to be measured something on y-axis, your height, something on x, and something on z. So we are living in 3D world and everything is to be represented, defined, and measured using 3 dimensions. However, when a particular object from 3D world is projected on a 2D screen, this is what we call as an image. This is how we can define image in the simplest possible case, that representation or projection of 3D object on a 2D screen. Similarly, we can have one more simple definition, that image can be defined as two-dimensional light dependent function, light intensity function, mathematically written as f of x comma y. This is very important, that representation for mathematical representation for an image, this is to be defined as f of x comma y. This x comma y, these basically represents two independent variables. It is very important from mathematical perspective that f of xy means some mathematical function. There will be some value, there will be some response, there will be some magnitude, which will actually depend upon x and y. Like we do have two independent variables, and this xy represents two independent variables in terms of rows and columns, horizontal and vertical propagation. So image can be defined as something having multiple rows, multiple columns, and then we will have some particular value. Just to make you understand at very beginning, let's see on the image, this image, particular image. Let us see this particular picture given on right bottom corner, that there is some light source, because it is very important. If there's no light, there will be no image at all. And even this is how human eye works. Human eye, human visualization process, this is how does it works. If there's no light, if there's no illumination, there will be nothing to see. We cannot see anything, or simple, there will be no image formation in our retina. So some illumination is there, and this illumination is throwing certain amount of light. This is particular object, and depending upon this particular dynamics, this particular object dynamics, light is being reflected back, and as a result some image is being printed on this 2D screen. So in real world, this is 3D object, and this is being printed, this is being reflected, this is being marked or placed onto the screen. So this is what we can refer right now as an image. So this now maps the true definition, that image can be defined as two-dimensional light intensity function. So as image is by nature, as image is dependent upon light, as image is light intensity function, and light is form of energy, therefore from like physics point of view, from mathematical perspective, we do have certain restrictions for energy. Light or energy, it cannot be negative, it cannot be infinite. Therefore mathematically we are going to pose restrictions, including 0 is less than whatever image represents is less than infinity. This simply defines very basic concept of physics, that energy cannot be negative, it cannot be infinite. Moreover, the image formation, this actually depends upon two different factors, and this includes illumination, that is light, and the property of the object. Illumination, this basically comes from the light source. We might refer sun, we might refer a tube light, we might refer maybe a lightning bulb, whatever. It might be natural or artificial, but there must be some light source in order to ensure that we will be having image at the output. Along with the imaging source, we need to have an object, and that particular object, it will have a particular characteristic, what we define as reflectance. So just to make things easy to understand, let's recall that we do have an ideal glass sheet. We do have an ideal glass sheet, and whatever amount of light is being thrown, this light will pass through the sheet because that is ideal transparent. Ideal glass sheet or ideal transparent sheet. So whatever light is being thrown, it will pass through, and as a result, we will not have image of that ideal transparent object. In contrast, if we do have a big, if we do have a heavy opaque object, so whatever light is being thrown, it will be blocked and reflected back, and that light will help us to see that particular object, or we will be able to recognize, we will be able to visualize that particular object from far distance. So the property of particular object, which basically determines whether there will be an image or not, this is what we call as reflectance. And on the basis of reflectance, we can categorize objects in two extreme categories: transparent, opaque, ideal transparent or ideal opaque. However, in the real world, there is no ideal. Therefore, all objects present, all objects found in this universe, in this world, they do have reflectance somewhere in between reflectance of ideal transparent and the ideal object opaque. Therefore, let us write this quickly, that f of xy, a particular image, this basically depends upon two components. First one, I of xy, is illumination or light, and second one, this is being multiplied with the reflectance. That there must be certain amount of light and there must be certain amount of reflectance. If any component of out of these two, if any component is missing, there will be no image. And as this light, I stands for illumination, illumination or light, as this light is form of energy, we are going to pose restriction. Energy cannot be negative, it cannot be infinite. And as this R represents reflectance, therefore reflectance will always be in between 0 and 1, that is ideal opaque and ideal transparent. So this is what I have been talking about, that reflectance is the light reflected back from object, and this always be in between 0 and 1. So once we have been able to obtain an image, as this image has been obtained using light, and light is form of like energy, and energy is continuous in nature, therefore by default the image formed is of analog nature. By default the image is analog or continuous in nature, and if we want to use a particular image in computer processing, we need to explicitly convert, we need to do explicit transformation from analog to digital format. Before trying to do the process of digitization, let us first define digital image. And digital image, it can be defined as simple, an image coming from analog nature, and we have performed some mathematical operation including sampling and quantization. Whatever input image is, when we are going to perform the process of digitization, this digitization, this actually consists of two sub processes, two sub steps: sampling and quantization. As a result, now we will have a two-dimensional, we will have a 2D matrix based representation for our input image, and this matrix based representation, this is to be termed as a digital image. So if I'm going to conclude this quickly, that a 2D image, it can be defined as a 2D matrix having multiple rows, multiple columns. How many rows and columns must be there? Now this would actually depend upon sampling, and this will be explained in the next slide. But just to give you a quick concept, that digital images can be represented in terms of a 2D matrix having many rows, many columns. And every single element, every single coefficient, every single value of the 2D matrix, this is termed as one pixel. This is termed as one picture element. Pixel or pel, normally we do use in short. This is representing the smallest part, the smallest component of a 2D image. And this basically defines a particular row and a particular column combination. I will show you this in next slide. Here it comes. The process of digitization, it can be defined as converting analog image into digital format, and this consists of two steps: sampling and quantization. When we talk about sampling, basically this decides that how many rows and columns will be there in the digital image. Whatever the size of input image is, we need to transform that input image into a 2D matrix having many rows and many columns, and how many rows and columns will be there, this basically depends upon the sampling. This is decided in the sampling stage, or maybe simply what you can refer is the resolution of image is actually dependent. This is decided, this comes from the sampling. And the appearance of a particular image, how much bright it will be, how much dark it will be, how it will appear on the screen, this will be based upon the quantization. So now let us talk first about the sampling. So digitization of the coordinates, rows versus columns, how many rows and how many columns, this refers to as image sampling. Normally sampling theorem is used in order to decide the size of the matrix, in order to decide how many rows and columns will be there. The more number of rows and columns will be there, the more information we are going to pack from analog image into digital one. The more information we will pack from analog image into digital one, more beautiful it will appear on the screen, but on the other end, it will also require more memory. So somewhere in the next lecture, we will also discuss about the relationship between resolution, rows, columns, and memory requirements. But just to make you understand quickly that the number of rows and columns are dependent upon sampling. The more samples we are going to take, more information it will contain from actual analog behavior. More beautiful it will appear on the screen because it will be good approximation, but it will require more memory as well. On the other hand, quantization. The quantization, it has nothing to do with number of rows and columns. Rather than this actually talks about what will be the coefficient values. Let us say we have done sampling and we have decided that our digital image, it will contain 4 rows and 5 columns. So in total, there will be 4 rows, 5 columns, 20 pixels actually. So in total, there will be 20 pixels. Now, what will be the value of those 20 pixels? Should it be 01? Should it be 0 to 5? Should it be 0 to 255? This is now actually dependent upon the quantization. So just to make things easy to understand, if we are going to allow only two values, let us say 0 and 1. So whatever number of rows and columns, total 20 pixels, all those 20 pixels, these will have value either 0 or 1. And when we will display that matrix as an image on the screen, we will be able to see only two behaviors. We will be able to see only two different colors. Maybe just to make things easy to understand, this is 0 for black and 1 for white. So having 20 pixels having 4 rows, 5 columns, but restricting our image to contain only 2 possible values. When we will display that matrix as an image on screen, we will be able to visualize and see only 2 behaviors or only 2 colors. Basically, that is limited information. However, if we are going to increase the range, if we are going to increase the range of values for our pixels, for our individual pixels, let us say that same image having 4 rows and 5 columns, we do have 20 pixels. Now these pixels can have any value in between 0 to 3. Now we have actually stretched our scale. Now instead of 0 to 1, now we have allowed 0 to 3, and as a result, at any given time, a particular pixel, it will appear either pure black for 0, 1 dark gray, 2 bright gray, 3 pure white. So like quantization, we actually decide what will be the range of values which we can assign to pixels, and the range of value, this actually describes the visual behavior of pixels on screen. How sharp image will appear on screen, this actually depends upon the range of intensity values, the range of values, the range of pixel values. And normally, in order to make things like fast from computational perspective, the range is normally chosen as an integral multiple of 2, like either 2 or 4 or 8 or 16 or 32 and onwards. So we'll talk in next lecture when we'll start working with gray levels or gray scale. But just to make you understand that during the process of digitization, we do have 2 sub-steps, sampling and quantization. Sampling is responsible for deciding the resolution or the number of rows and columns, and quantization is responsible for deciding the gray scale, or simple the range of intensity values to be used for individual pixels. So coming back, as I mentioned earlier, the digital image is actually an approximation of original image in terms of many rows and many columns. If you can see, this is row number 0, row number 1, 2, 3, many rows and many columns. And every single particular element, this particular matrix, this 2 comma 1, this represents second row column 1, this 1 comma 2, this 9 comma 2, whatever this is. So every single element, this represents one particular pixel or one particular picture element. And overall, this is the approximation of a 2D image for computer. How does it comes? Maybe this is like something easy to understand, that we do have an analog image and it is like of very good quality. We do have a continuum image, we do have an analog image as shown, this blob on left hand side. And if I'm going to do the process of digitization, the very first thing is I have to decide total number of rows and columns, that is sampling. Let us say I have decided that this particular input image, it will have, just for instance, it will have 15 rows and 12 columns. So I have created this grid, and then I have to map this particular image onto this grid. I have to do approximation of this input image in terms of this 2D grid. And accordingly, I do have this particular image. If you can see, now this is comparatively degraded, or the quality of this digital image, this is not as fine as it was in original case. So depending upon sampling and quantization, a general theme is that the image quality of like output image or digital image, this will be comparatively less, it will be comparatively degraded from the original one, because we are going to do approximation. Yes, we can keep on increasing sampling, and as a result it will keep on increasing the image quality on the screen, but it will also keep on increasing the computational requirements and memory requirements. So this is what digital image representation, and this is what an extended example, that input image, certain amount of light is being thrown, and this is a lens, maybe human eye or maybe camera lens, and this input image is being placed on 2D screen, and then this is further being mapped on a 2D grid, and this is what digital image or a 2D digital representation of actual image. This one in the center, this is analog image or actual image, and this is the digital approximation, and we can see that due to the number of sampling, due to the number of rows and columns approximation, comparatively the quality has been degraded. This was dependent upon sampling. However, we can also see the brightness or the appearance or shade or the coloring. We can see a noticeable difference over here in the digital image in comparison with the original one, and this is based upon quantization value or quantization scale, what range of intensity values, what range of pixel values we have allowed. So more values we're going to allow for quantization, more sharper and more smoother behavior it will give us, like more improved, more attractive it will be, more consistent it will be. The less quantization values we are going to use, bad approximation it will give us. Just to make you understand, let us say we do have a simple one matrix, and this is binary matrix. It is having 6 rows, 6 columns, 6 rows and 6 columns, and all these values are simply, we are using a very restricted range 0 and 1. As a result, all those pixels which do have intensity value or pixel value 0, they will appear black on screen, and all those pixels which are having intensity value or pixel value 1, they will appear white. And this is just to make you understand that sampling and quantization, they are very important in overall deciding that how image will be appearing or how the image will be visualized on screen. Sampling represents number of rows and columns. The more rows and columns are there, the more sharper it will appear. And quantization, this refers basically the appearance. The more values we are going to use in the quantization scale, more colors it will produce, it will generate on screen while visualization. This is what, if this matrix is to be considered as an image, this is what it will be displaying on screen. So this is all for this particular lecture, where we have seen the basic representation of input image, memory representation of digital image, and I have also provided the corresponding video where I'm using MATLAB in order to demonstrate all these concepts, whatever we have talked. Thank you very much, and we'll start talking about grayscale and resolution in our next lecture. Thank you very much.